It's my great pleasure to introduce Dorin Bucur from Savoie Mont-Blanc University. What a nice name, in Chambéry. And we're going to talk about spectral shape optimization problem with Neumann condition on the free boundary.
Thank you very much. It's really a great pleasure for me to be here for this week. So I will speak about shape optimization problem, and let me explain the words inside the title. Precisely, so I'm interested to find a geometry, a domain, which satisfies properties in terms of the eigenvalues of some operator set on the domain. In general, which will be the Laplace operator. So So I will speak about shape optimization problems, and the idea is that we want to find the best domain, the best geometry, which satisfies some good properties in terms of the eigenvalues of some operator. So I will discuss only the Laplace operator, but I want also to say some words about Neumann boundary conditions. So you see, you want to find the best domain for which, let's say, the first three eigenvalues are very low or something like that. And you have some boundary conditions. And the boundary conditions may be of different type, of course. And depending on the type of the boundary conditions that one has on the free boundary, on the unknown part of the boundary, different mathematical worlds start to open. If you discuss, for instance, Neumann boundary conditions, this is somehow very close to homogenization. If you discuss Dirichlet boundary conditions on the free boundary, this will be very close to the theory of free boundary problems, and the analysis tools come from the work inspired by Alten and Caffarelli in the 80s. On the other hand, for instance, if you have on the free boundary Robin conditions, it's a third world coming into the game, because this problem transforms into a so-called free discontinuity problem, and this was initiated and invented by Ambrosio and De Giorgi in the last 80s for dealing with the Manford-Schacht problem. So depending on the boundary conditions that you have on the unknown boundary, different mathematics enters into the game. So here I will discuss about Neumann conditions, and I just want to say that this is the case where we know the less information on the problem. And my co-authors are Antoine Honreau from Nancy and Edouard Audet from Grenoble. And I will present some results obtained separately with my co-authors. So let me start and introduce the problem. So omega will be the unknown geometry, but let's start and assume for now that omega is a bounded, open, and Lipschitz set, and not necessarily connected. I will explain why I particularly want to deal with non-connected sets. And I'm looking to the Neumann-Laplacian on omega and to the eigenvalues, precisely minus Laplacian u equal to mu u in omega, and with Neumann boundary condition d over dn equal to 0. Now, under the assumption that we have here that omega is open, bounded, and Lipschitz, we have compact embedding of h1 in L2 of omega, and the spectrum of the Laplacian with Neumann condition is a spectrum consisting only on eigenvalues. Then we count together with their multiplicity. And the first one is always 0, corresponding to a constant eigenfunction. Well, the second one, and here one has to be very careful to the sign, the second one may also be 0, for instance, if omega is disconnected. If omega is connected, the second one is definitely strictly positive. Okay? But here I say that I really need to understand this peculiar situation in which I'm looking to the spectrum of a geometry which becomes disconnected, because at some point I will leave the sets to be completely free, and they can break into pieces, and then the spectrum will be this kind. So I will have 0, which higher multiplicity. And the generic question that I will try to answer can be formulated like that. I'm looking to the kth eigenvalue of the Neumann-Laplacian, and I want to maximize the kth eigenvalue among all Lipschitz subsets of Rn with prescribed measure. So this is a generic problem to which I want to give an answer. And of course, the lower eigenvalues are more important, but in general, let's take a look to this problem for every k. And because we have good homotopy properties, scaling properties of the kth eigenvalue of the Neumann-Laplacian, this problem can be reframed in a scale invariant framework. as the maximization of the product between the measure of omega power 2 over n times mu k of omega. And this is there is no any more measure constraint on this problem. And this supremum, which is finite, it can be easily proved is finite, will be called mu k star. But the question will be here to understand whether or not this shape optimization problem, because the unknown is the geometry, this body omega, has a solution, and probably to understand whether or not we can say something about the shape of the solution. So that's the generic problem. And now let me go a little bit into the history and start with the first result in this sense, which was given by Szego in 1954. And Szego proved that the disk in 2 dimensions, only the disk in 2 dimensions, maximizes the first non-zero eigenvalue of the Neumann-Laplacian mu1 under a measure constraint among smooth and simply connected sets. So this is the first inequality. It concerns the first eigenvalue, and it was proved only in 2 dimensions under this topological assumption, simply connectedness. And now let me mimic in a few lines how the proof of Szego works in order to see what kind of problem is. You see, the problem we are dealing with here is to maximize eigenvalues. So maximization of eigenvalues, in fact, if you know that mu1 it's a minimum of its Rayleigh quotient, it's a max-min problem. It's a max-min problem. And this is, from the analysis point of view, a little bit difficult, because dealing with the max-min and making perturbations is quite complicated. But from a geometrical point of view, geometers are much happier with these kind of problems, because if you want to prove that a specific geometry is better than the other one, because of the structure of the problem and because of the Rayleigh quotient coming into the game, it's enough to construct a magic test function. Let me tell you what this means. So we have here omega. We are looking to the first eigenvalue of the Neumann-Laplacian on omega. Here I have the disk of the same measure, because that's a measure constraint. And I have the first eigenvalue on the ball, and what one wants to prove is that mu1 of omega is less than or equal than mu1 of the ball. And for that, because mu1 itself it's a minimum of a Rayleigh quotient, it's enough to find a suitable test function. So if by some chance one is able to build a function, let's call it psi, such that I have this inequality here, so I'm writing the Rayleigh quotient on psi associated to psi on omega. So if I'm able to build only one test function, psi, which is admissible on omega to be test for mu1, then automatically one has this inequality. But here is the mathematical question. If this test function satisfies also the second inequality, then we are done, because this function will tell me as an intermediate step that mu1 is less than the Rayleigh quotient, and provided this is true, we have the inequality. So what do we ask for psi to be test? Only orthogonality on u0, on orthogonality on constants. So let me write it like this. So integral of psi times 1 on omega is 0. So if one finds such a function, this inequality is immediately satisfied. And then if the function is good, it's chosen in a smart way, then this inequality will also be satisfied, and we are done. So the problem here is just find a suitable test function. And now how proceeded Szego in 54? He used the hypothesis that he works with simply connected sets, and he built a conformal mapping from the disk onto omega, and then he built test functions inside omega starting from the eigenfunctions from the disk. So he said, okay, let's take the 2 eigenfunctions corresponding to the first eigenvalue on the disk. So it's of multiplicity 2. I will show you the geometry of the eigenfunctions later. Then he transplanted these eigenfunctions in 2 functions here, psi1, psi2, with the help of the conformal mapping. And now, and here is an argument which is a little bit tricky, these 2 functions do not necessarily satisfy orthogonality on the constant, but choosing well the point where the center of the disk is placed into omega, he achieved to have orthogonality on the constants. And then he uses again the fact that these are coming from eigenfunctions, and he proves this inequality, and this is less than mu1 of the ball. So this is the idea of Szego. So he built the functions from inside, and he built this, let's call it magic test function. Nevertheless, 2 years later, Weinberger proved the result in fact holds in Rn, and without any topological constraint. And the proof of Weinberger is again somehow of the same type, now in Rn, and he wanted to build test function on omega in the same way, some magic test function starting from the ball, only he doesn't have any topological constraint. And you see here it's a little bit tricky in the sense that you cannot build from inside a function, a test function in omega. And I will show you, I will detail you a little bit later how Weinberger built these functions from outside. Nevertheless, years passed, and it came a problem concerning the second eigenvalue. And in fact, Girouard, Nadirashvili, and Polterovich in 2008 proved that the union of two equal and disjoint disks maximizes mu2, again with a measure constraint, in 2 dimensions in the class of smooth simply connected sets. Okay, so now this is the second eigenvalue, and you see already when you look to the statement, you compare two disjoint disks with a simply connected set. So it's a little bit strange because the simply connected a priori it's assumed to be connected, but in fact they proved that for any simply connected set, its second eigenvalue is less than the second eigenvalue of the union of two disks, strictly. And he proved that taking two disks which just are touching on a very small pieces and you just move them to disconnect, you achieve the supremum. This was the result of Girouard, Nadirashvili, and Polterovich. But now you see the question is a little bit different, because here now you have two disks of equal measure. The sum of the two measures makes the measure which is allowed for omega, which is now simply connected, and they wanted to somehow to build again test functions, but here with the inequality for mu2. Okay? So their problem was something like that. They want to have mu2 of omega less than suitable test functions, and here mu2 of the union of the two balls. Okay. How to build this? How to build this starting from a disconnected set? You want to build test functions on a simply connected set. And they had really a very, very smart idea. So the idea was to take only one of the two disks, u1, u2, make a conformal mapping on a hyperbolic cap from one disk. So with this conformal mapping, build some functions on this hyperbolic cap, then use reflection to extend the function on the complement of the disk, and then with the conformal mapping obtain two test functions psi1, psi2 here. Okay, so this somehow mimics the case when you have the two disks which are touching on a small, very small piece of geometry. And then the question is, with this psi1, psi2, do we have first this inequality? And the answer was yes, we would have this inequality provided orthogonality holds, because you have to be tested for mu2 now. And also there are several ways into the Rayleigh quotient on how to look to the construction of the second eigenfunction. And they chose the way which is the following. They had orthogonality on constants. They wanted to have orthogonality on constants, and L2 orthogonality among them. Orthogonality in L2 because the one in H1 is for free. So roughly speaking, they required three equalities, and they achieved this by choosing in a good way the size of the spherical cap and the position of the center of the conformal mapping. Okay, well, that's easy to say, but it's complicated to prove. And the mathematical argument to prove that this works, ultimately works, is based on a fine topological result. Okay. So this is the result of Girouard, Nadirashvili, and Polterovich from 2008. And to go further, let me just say that Poliquin and Roy-Fortin in 2010 proved that mu22 is not maximized by a ball or union of balls. Just not to think that for every k, the maximizer is a ball of union of balls. For the Dirichlet-Laplacian eigenvalues, it was known already from the fifth by Edouard Roudet that is not minimized by a disk or union of disk in 2 dimensions. But here it's a little bit more tricky for the Neumann-Laplacian, also because of numerics, which is done to complete. And now why people look in spectral geometry to this question? Because this question of maximization of Neumann eigenvalues is related to a very famous conjecture by Polya. And the conjecture by Polya states that for every index k, the kth eigenvalue of omega is bounded from above by the main term in the Weil asymptotic formula. So you have the Weil asymptotic formula for the kth eigenvalues, but the conjecture states that the main term is also an upper bound for the kth eigenvalue. So this conjecture reads like that. In general, the conjecture is open. It is known for mu1 because of the result of Weinberger. So for the first one, it's true. It's known for any k, but only for small class of domains, like for instance, tiling domains. But in general, it's open. In general, it's open. So equivalently, with my notation, this would be mu k star less than this quantity. Mu k star, it's the supremum of mu k of omega times the measure power 2 over n. What was proved, so people really try to prove this conjecture by different ways. There is a result by Kroger, who proved that there is a bound, but with a number here which is in general larger than 1, but it's only dimensional. And there was a result by Colbois and El Soufi in 2015, where they justified that Polya's conjecture is equivalent to understand only the asymptotic behavior of the maximizer of the geometry, which maximizes mu k. In fact, not of the geometry, of the value. But in order to capture this asymptotic, the idea is somehow to prove that the best geometries do converge to something. In general, you expect to have the disk. Of course, this would be a way to prove Polya conjecture, but for that you have to understand what is the geometry optimal for mu k, and whether or not into the asymptotic, when k goes to infinity, this geometry somehow turns to be closer and closer to the disk. There are some very partial results in that sense on parallelepipeds and particular geometries, or for some different functionals, not mu k, but some race means and so on. Okay, so now what I show you here are some numerical computations by Antunes and Ude in 2017. And what you see are the best computed geometries, minimizing, here is mu1, it's the disk, that's the Szego-Weinberger result. That's mu2, that's the result by Girouard, Polterovich, and Nadirashvili. That's 2 disks. And starting from mu2, well, that's the question. We don't really know what happens, but at least from a numerical point of view, one can try to use tools from shape optimization to maximize those eigenvalues. And this is the maximizer coming out from for mu3, mu4, 5, 6, 7, 8, 9, 10. Well, now you see, people did the same. I will show you immediately some pictures also for the Dirichlet-Laplacian, and there is something to say here. So the numerical results are really very stable for the Dirichlet-Laplacian. I mean, people in different groups, in different places in the world, by different methods, computed those best shapes by different methods. While for the Neumann-Laplacian, the results are rather unstable. I mean, at least for the 7th, there was a huge debate, and it is unclear what is the best geometry, because people cannot decide between this one, now that's the latest hope, and another one which is connected but with a small hole inside. Okay. Okay, so this is a numeric. These are numerics. Here is some numerics in 3 dimensions, and in 3 dimensions, you find the result here of Weinberger for mu1, and surprisingly or not, you find that in 3 dimensions as well, the maximizer for mu2 it's 2 balls, and so on. Okay, and so on. And now I will try then to tell you what we have worked in this direction to prove existence of a solution. Well, we didn't arrive. And then to prove that in general this is true and the maximizer is indeed 2 balls. But before that, let me put you one slide on what occurs for the Dirichlet-Laplacian. So for the Dirichlet-Laplacian, the problem is to minimize the eigenvalues. The first one is the disk, or is the ball, is the so-called Faber-Kran inequality. The second one, it's 2 balls. It's called the Kran-Szego inequality. The third one, well, in 2 dimensions, its conjecture is a disk. In 3 dimensions, it is not the ball, but one doesn't know exactly what it is, and so on, and so on. And what I want to say is that there was really a lot of research, and even nowadays, people is looking to understand what are the qualitative properties of those geometries, of those shapes. And maybe the first result in this sense was by Butazzo Dalmaso in '92, where they based on the full relaxation of the problem, they proved existence of a solution of a minimizer for this problem, provided that all omega stay in a bounded box. Okay, and so this result is very, very important by Butazzo and Dalmaso because it's first of all, it's a very general result. It applies to lambda k, but not only. It applies to functionals depending on eigenvalues. I'm just speaking about lambda k because it's an easy example, but it applies to, and this result was based on the full relaxation of the problem. What does it mean? It means that for the Dirichlet-Laplacian, if you have just an arbitrary sequence of open sets in a box, for a suitable chosen subsequence, you are able to say where the spectrum goes, point by point. And what does this mean? This means that they can build a so-called capacitary measure. So the limit set, it's not a set. The limit, it's a measure. And they define the spectrum associated to this measure, and they know exactly what happens. And this, based on that, they prove the existence of minimizers in the sense that they prove that the measure, in fact, it's corresponding to a real geometry. And since then years passed, because people wanted, in spectral geometry, wanted to remove the box. Of course, you want to know that the minimizer is the disk. You know, the minimizer is the disk for lambda 1, but then for another set, if you have a box and then you increase your box, would the minimizer be the same or not? No. And it was a long story for that, and there was 2 proofs by Mazzoleni and Pratelli and by myself, where we proved that one can indeed remove the box. And you get existence of global minimizers in Rn for the eigenvalues of the Laplacian. Moreover, all minimizers, all those geometries are bounded sets, have finite perimeter, and do satisfy some densities. So, and since then there is even now intensive research to understand what is the regularity of these free boundaries. And as I said, these problems with Dirichlet boundary condition enter into the theory of free boundary problems and somehow can be analyzed through Alt-Caffarelli techniques. And first of all, we have proved with Mazzoleni, Pratelli, and Velichkov that on the optimal set we have Lipschitz eigenfunctions, but we couldn't prove that the optimal sets are open. Then Mazzoleni, Terracini, and Velichkov, for the sum of eigenvalues, they really proved that the set is smooth, and they found the structure of the singular set of the boundary. And there was a very recent result by Fan Kualin and Denis Kriventsov, who for lambda k, exactly not for the sum of eigenvalues, they give a detailed structure of the singular set. Okay, so this was just a parenthesis to tell that for Dirichlet boundary conditions, there is really quite intensive research, even right now, on the question. While for Neumann boundary conditions, there is almost nothing. So let me just raise the question of existence of a solution for this maximization problem, for this shape optimization problem in general. So for mu1, we know it's the disk. For mu2, I will discuss it. But starting from mu3, we just don't know. And not only that we don't know what's the direction to take. It exists or it does not exist. This is really an unclear question, because similar problem in elasticity, for instance, in the structural mechanics, you optimize structures with Neumann boundary conditions on the unknown boundary. In general, when you minimize compliance, you don't have existence of a solution, you have homogenization. What really makes a difference? Because when you look to this problem to mu1, you know that this doesn't occur. It's the ball. So you don't have this phenomenon. We don't know. Nevertheless, even without existence, Polya conjecture could possibly be proved, provided that one knows the asymptotic behaviors of mu k. And in general, so I said this is somehow close to the homogenization theory, but the difference here is that we really deal with void. So, of course, for numerical purposes, one can try to say to optimize the best geometry, saying that you have a domain and the complement it's a sort of soft material. But from a theoretical point of view, we really deal with void. So we cannot replace the void with a soft material. So, and this makes that this problem it's somehow very bad, because you have a domain. They are Lipschitz set, but they can move in some way into the limit. What do you have? Nothing, because the sequence of Lipschitz sets can converge towards anything. So you cannot extend functions. So the space H1 extended outside, it's not stable. So what do you do? That's the crucial problem, and you want to understand this from an analysis point of view. Okay. And so let me tell you a tentative way to prove existence. So we don't know the exact relaxed formula on what a sequence of geometries do converge. We don't know that. So what we try, what we can call over-relaxation. So to change a little bit our problem, and hopefully at the end possibly to recover an existence result for the original problem. And what is the sense of this over-relaxation? So the idea is that we want to replace our sets, which are bounded and Lipschitz, by densities. So I will replace a set by a function, which is here denoted rho, is defined on Rn, and takes values between 0 and 1, and it's in L1. So what you have to have in mind is that if I'm working with a real geometry, the density rho is the characteristic function of the set, which is 1 in omega and 0 and outside of omega. And to this density rho, we associated this value that we can call mu k tilde of rho, which is defined following the Rayleigh formula, with a difference that is not anymore a min-max, it's an inf-max, inf among all subspaces of functions of dimension k, which are orthogonal to rho in Rn, and max over all functions belonging to the subspace. So, and very important, in the Rayleigh quotient, the density rho appears to the numerator and to the denominator. Okay, so what's the point with that? Imagine that instead of rho, you plug the characteristic function of a bounded Lipschitz set. If you put here a bounded Lipschitz set, then exactly what you will find from this, exactly the kth eigenvalue of the Neumann-Laplacian. So there is no difference, provided that rho corresponds to the characteristic function of a Lipschitz set. What happens if rho is something else? It may be, for instance, the characteristic function of a non-Lipschitz set. And that's very bad for the spectrum of the Neumann-Laplacian, because on a non-Lipschitz set, the spectrum of the Neumann-Laplacian may not consist of eigenvalues. It may be continuous. So that's very bad. Or rho may just be a density without really any property, without bounded support or anything else. So to what this geometric quantity, or this, let's call it variational quantity, corresponds? I don't know. The answer is I don't know. But what I know is that the main risk comes from this infimum. So if, for instance, the geometry is not Lipschitz. I have a domain, a characteristic function associated to a non-Lipschitz set with some cusp and something like that. The risk I'm taking is the infimum here is 0. That's very easy to achieve. So is the current Hilbert example showing that you have a square of edge equal to 1, and then you attach a small square with a tube where the size of the width is epsilon third and all the other sizes are epsilon. The first eigenvalue, for instance, goes to 0 as low as you want, being this a sort of pointwise perturbation at the boundary. And you can do this with several, with k squares, and you will have k eigenvalues as close to 0 as you want. The point is that we don't want to have this, because we want to maximize the kth eigenvalue. That's a good problem, and so we expect that this very bad phenomenon will not arrive in the optimization process. So what we can prove, and that's a sort of preliminary result, because we don't know to say many more things about that, is that if we take a box, so we cannot remove the box for compactness reason for now, then the maximization problem of this kth pseudo eigenvalue associated with density rho with a mass constraint, so the volume of omega is transformed into the mass of the density equal to a given number c, then we have the existence of the best density in a box. The key question is it true or not that the density that we have at the optimum corresponds to a geometry, it is of the type 0 and 1 to have a characteristic function, and not only that the boundary of this geometry is smooth enough to ensure that it's really a kth eigenvalue of the Neumann-Laplacian. So that's the key question, to which we don't have an answer, unless, and I will show you to the cases where k equals to 1 and 2. And there is a second question, which for the Dirichlet Laplacian it took 20 years to answer, is can one replace the box D by Rn? And again, that's I don't know really how to deal with that. Okay, so that's an existence result. And now let me show you some numerics, because of course we have a guess that possibly this is true, that working with densities will lead to the same problem. And here is some numerics done by Edouard Roudet, where he started to optimize densities in the spirit that I showed you before. He starts with a random density, and it naturally pops up at the optimum the ball, the disk in 2 dimension. So that's numerics. So there is this segregation of the density towards values between 0 and 1, and we don't know how really to explain why this occurs. But this is just numerics, and this is quite stable. I mean, starting from different random densities, there is always segregation towards the disk. It's very nice. And this was in fact inspiring for the theoretical result I will show you immediately. And secondly, he did this computation for mu2, and again, clearly, the geometry which appears, it's the 2 disks in 2 dimension. Of course, there is some intermediate value at the interface. Well, okay, that's numerics. But this is again was very stable. So numerics show that starting from random densities, the maximum was achieved for mu2 on 2 disks. In particular, this says it gives the intuition that into the result of Girouard, Polterovich, and Nadirashvili, you don't need to impose simply connectedness a priori. So the result holds in the class of simply connected domains, but working with densities, you remove absolutely any topological constraint. Okay, so let's go on. And surprise. I don't know how to interpret that. We don't know. So this is the maximizer for mu3. If you look to the region where this is 1, this is very close to the shape obtained numerically by Antunes Freitas, and previously there were some other results. But from a numerical point of view, we have this region here that we don't know how to interpret exactly. It's only because of numerics. it is because we work with a soft material and not with really with zero on the other hand? We don't know. Because this is crucial somehow, because if we would have the conviction, we would be sure somehow from numerical point of view, we would be very happy to know that we have existence of the best geometry, but this is unconcluded for now. So, we don't know. This is the result for mu4. Now,
the simulations that we have seen, the two-dimensional simulation we have seen before, they had the sharp corners, and so they were really the intersection of three poles, or
so so you mean this one?
Yeah.
Well, the corners are not sharp here, not sharp, but because maybe the numerics. So when you maximize those eigenvalues, there is a conjecture which says that at the maximum, all eigenvalues are multiple. So from a numerical point of view, when you deal with multiple eigenvalues and you want to perform shape derivative and to optimize them, it's very, very problematic. So maybe this is the reason they do not see here corners, and this is the reason that we have there this transition part. We don't know. We don't know. And again, this is really a problem. It's the multiplicity. Here we have the same difficulty. So that's for mu4. More higher is the eigenvalue, these portions are larger, but nevertheless there is this segregation towards a huge part of the domain. I mean, and this is stable and disappears often, and that's for mu6. Okay, so now let me tell you what happens for mu1 and mu2. So, and for that, let me in some words describe what was the idea of Weinberger to prove that for the first eigenvalue, the maximum is achieved on the ball in any dimension. So in any dimension, one cannot use any more conformal mappings of this kind. You don't have any constraint on the topology. And the idea was to build the test function omega from the outside, not from the inside of the domain. What means build from the outside? The idea was the following. First of all, take a look to the eigenfunctions corresponding to mu1 on the ball. So on the ball, the first eigenvalue, it's multiple of order n, and all the eigenfunctions look like that. It's a radial function multiplied by xi divided by r, where the radial function satisfies some differential equation here. So there is a sort of orientation of these eigenfunctions. And the idea of Weinberger was the following. So he has the eigenfunction onto the disk, which have that structure, radial function times xi over r, was to extend, first of all, the radial function to be constant to its value from the boundary of the ball. So this function j is extended constantly outside. And then to test with the new functions which are obtained in this way, he takes this extended function gr, and for some point, for some center a into the plane, you have the function, vectorial function ax divided by the distance to the point. So in fact, we mimic xy over r with the origin. Okay. So this was the idea of Weinberger to construct this package of n test functions. Roughly speaking, starting from the one of the disk is placed somewhere into the point A, then we extend constantly j, and we keep xy over r, which is here. And the idea, he said, okay, let's take these test functions, which are now starting from the ball, they are defined over the full space. Now, we try to take the traces of those functions on omega and to use them as test there. So these are the test functions that we shall use on omega, is the trace of this extended function from the ball. So here is somehow how the geometry of this test function is. So you have the ball, inside there is its original eigenfunction. If this is a vector v, now from outside this function is here, so on this line is 0, here it's odd, and here it goes up to 1, and then it's constant, and then it's constant equal to -1 on the other side. And now you can change the orientation of this vector. Xy will be the one given by the eigenfunctions, but of course this is a linear space, so you can take any direction and in this way tune the direction of this test function. And now again, the point was, okay, we extended, we found some test functions here, but are they good? Well, what means they are good? They have to be orthogonal to constant, first of all. And to prove that there is a position of the disk such that these test functions are orthogonal to constants, there was again a topological argument. Weinberger used the Brouwer theorem to justify the existence of a position such that on omega these functions are orthogonal all to constants. So that they can be taken as tests for mu1, and by summation one arrives to some computation, and surprise, what appears is that at the end you finish only with the radial functions to the numerator and denominator. Okay. So this is what one gets. Crucial question: is this less than or equal than mu1 of the ball? And the answer is yes, and is yes, because analyzing the ingredients appearing to the numerator and denominator, one observed that to the denominator the function is strictly increasing and to the numerator is strictly decreasing. This means that more or less we are in this situation. Here is the ball, here is omega, and we want to compare the Rayleigh quotient onto omega towards the Rayleigh quotient onto the ball with the same function, because this package onto the ball, it's exactly the one which gives the eigenfunctions onto the ball. And for that, point by point, we see that if we displace the mass from the red region towards the green region, it's a mass displacement argument, then these inequalities go into the right sense. Here, this is decreasing and this is increasing because of the monotonicity of the two functions. So this ends with a mass displacement argument. And this proves that indeed mu1 is maximal on the ball. And now here is the result we have proved. So I will split it in two. So it's a joint work with Antoine Onro. And we proved that if omega is a smooth Lipschitz set, then mu2 is always maximized on two equal and disjoint balls in any dimension of the space. And so how did we prove it? Because somehow we face the same difficulty as Weinberger towards the proof of Szego with simply connectedness. So the idea was here again to build suitable test functions, and these test functions should be in such a way that, for instance, any two balls would give optimality, or any two balls possibly connected by a very thin tube and with a low eigenvalues. And you see, and this is the main difficulty, how to build suitable test function. And what we have done, starting from the one test function of Weinberger, we decided to take a hyperplane, to cut out one of the two halves, we keep the one with the center, and then to reflect the Weinberger test function onto the other side. In this way we get a sort of this kind of geometry where we have two poles, and moving the poles, all the eigenfunctions move, or moving the orientation, again, eigenfunctions, test functions change. So roughly speaking, this is the geometry. We have the poles, we have the orientation of the eigenfunction, and we can formally build, as previously, a sort of vector-valued function, depending only on the center of the poles, which is this one. This involves a symmetry operator, because we have here a reflection. And with the help of this, we can build test functions. So our test functions, as Weinberger, are of the following type: is this vector-valued function depending on the two poles times scalar product times EI. And this gives us a package of n test functions. What is our freedom is the position of the two poles, and of course their orientation into the space. Okay, question: are these set of functions good to test for mu2? What do we want if we want to test on mu2? Well, these functions are good tests on mu2 if they are orthogonal to the first eigenfunction, which is constant. So here I have that the sum over omega of this is 0. And if they are orthogonal on the first eigenfunction, which is u1. So this is what we require, and if we have that, we can use them as test function. So in other words, we require more or less the same package of equalities to be 0 as Weinberger, but we do require something new, because we require orthogonality on u1. And u1, it's an unknown function because it depends on omega. It depends on omega. And in fact, this idea, we had it for maybe for 4 or 5 years before. But we were not convinced whether or not this can be done. And at some point, with Antoine Enro, we said, let's do numerics. Let's try to take some geometries and to test whether or not for this geometry we can find good points A and B such that those functions are really, numerically speaking, orthogonal on 1 and u1. And the answer was, in all of them, it worked. So I said, okay, this should be true probably. And now here is how the geometry of this test function. You see, there are two poles, and here they are tuned to be opposite, and here they are tuned to be parallel. And they glue on the hyperplane in the middle. So now, if one finds the position of the 2 points, A and B, to prove the inequality goes pretty much in the same way as Weinberger, because taking them as test, if they are admissible, we achieve this kind of inequality. Now we split carefully these integrals over omega into the left-hand side and right-hand side, because now there are two pieces which act somehow as parts of Weinberger functions. So the geometry will be something like that. This is our test function. You will observe that the sum of the measures of the two pieces of ball is in general lower than the measure of omega, because the sum of the measures equals, but they overlap. And again, we have to produce a sort of mass displacement argument, which is only formal because these pieces are missing. But nevertheless, we can achieve the inequality. So the technical point which remains to be solved is whether or not there exist points A and B to have orthogonality. And now here we use a topological degree argument. We introduce the function depending on the 2 points A and B that we wanted. It's exactly our its two n components are the numbers that we want to achieve to be 0, and we wanted to prove that we can find a couple of points A and B such that f and A and B equals to 0. And for that we made a double deformation of the function, a continuous deformation. First of all, for the first n places, we got rid for the last n places, we got rid on u1 from u1. So this was the idea, to get rid from u1, to transfer this information towards the integral of the function without u1 on some suitably chosen ball. And in the first one was to get rid of omega, in the first package, again towards integral of some another well-chosen position of the ball. So what we proved is that indeed we can find two balls such that this deformation of the function is continuous, and there is no 0 crossing the boundary of the definition domain. In order to take a look to the topological degree, we had to understand what are the zeros of the limiting function obtained here for t equal to 1, and we observe that we always get 2 zeros, which in fact are the centers of the ball B star and B sharp, and we computed the sign of the Jacobians, and both of them were negative. So we concluded that the topological degree of the function at 0 is 2, and so we have at least one 0. And this achieves the proof. Nevertheless, now the question was, okay, but what happens with the densities? And the answer is, well, surprise or not, this occurs also for the densities, in the sense that if instead of the domains now we work with densities, we still have the same inequality. So the maximum of mu tilde 1 in the class of densities of a given mass, it's always achieved on one ball corresponding to 1 and 0, and the maximum of mu tilde 2 for every density is achieved on 2 balls of mass of equal mass. And so this means that we have existence in the class of densities, and the supremum is the same either in the class of densities or in the class of Lipschitz sets for a ball and one ball. Okay. Yeah.
So you had an assumption that because you were working on a finite on the domain D, so
Yeah.
it must contain two balls that does not touch the boundary, or
No. This was only for the existence part. This result is true in general because here we make a direct comparison. So it is worth to say that to prove this result is not the standard proof that I would have liked to give, but I'm not able. Is that the standard proof would be, okay, let me prove existence in general of the best row without the box. Try to understand from optimality what are the good properties of row, find extra condition of row on row, and then prove it is the ball or two balls. Is not the way that we took. So these results are obtained in a direct manner. So we reproduce the argument of Weinberger, the one with the two balls, directly on densities.
any density.
On any density, not only bounded, so just any density. So thank you for your attention.
Thank you. Very much. Time for questions. Yes, great, please.
Nice talk. I was wondering, in the comparison of the numerics, when you have the density and without the density, what did the numerics show as far as what was the lowest? I mean, I guess there was explicit formulas for the eigenvalue in both cases. You know. For example, for the 3-disk one, overlap.
So the numerics here,
Yeah.
so the numerics, so the value obtained here is higher than the value obtained doing classical, let's say, shape optimization. It's higher. Nevertheless, we said, okay, let's take a look from this and just try to extract the geometry with corners, and then directly compute the eigenvalue, the third, on this geometry, and compare with the best numerical computation obtained by the shape optimization argument. And it was not the best. So, the one obtained by shape optimization methods was better.
Yeah, but if you remove this region,
exactly.
that's the right volume.
Exactly, it's exactly what we did. So the
But you don't have the right volume.
Oh, no, we rescaled.
You risk.
Yeah.
So it's numerical noise.
I don't know.
No, it's density. It's thin.
Yeah, but these, for example, these points there, yeah, that artificially increase your eigenvalue, or in some sense, right? Yeah.
It's better.
So if we remove them in our computation, it's worse.
So is it the analysis model then correct, or is it maybe something like the checkerboard that you see that the analysis model cannot
No.
physically find?
Well, if I that's you to understand, but it's another relaxation. It's not a true relaxation.
Okay. So that's the question. So what is surprising is that for 1 and 2 is the same fact, but the proof is not done by density. I mean, by it's totally different. So we just don't know.
Yes, please.
But maybe I missed this comment. So about the box that you used to.
Yeah.
What's the reason why you cannot prove the result without the box? So what
Okay, so I can tell you exactly what happens for the Dirichlet problem. So when you minimize in a box, you have good compactness in general, compactness of H1, 0, and L2, and so on. Here, if I'm in a box, I have good compactness in L star infinity, so I don't have pieces which somehow live towards plus infinity. So the density remains concentrated in the box. If I'm working without the box, then imagine that there are pieces of geometries or densities which are running away very far away, so they do not concentrate the mass. So what can I do? In the Dirichlet case, we prove that cutting these pieces and then rescaling the geometry is better. For the Neumann problem, I don't know. So there may be pieces which are somehow going. I don't expect that, but yeah.
But do you see this in the
numerics? No.
In the numerics?
No. The numerics. You have a box, and
No, but you always touch the box.
so yeah. No. This is not touching the box. What you see, it's only the picture that we took outside.
Okay.
But
In
if
numerics,
we have
you
a
take a
big box,
box, touch
they
enough,
will be
you
inside. Yeah.
I have, before we go to Yeah, so in the numerics, this was done by Girouard, I guess.
Yeah.
Did you use a specific formula to take care of the multiplicity of the eigenvalue? Because when you converge, probably the third eigenvalue here is multiple, so you should not use a standard gradient, but rather some kind of subgradient.
I cannot answer this question, but it was we were very aware about that. So probably
Yeah,
he took. Yeah, we'll ask him. Yeah.
And then a final question is, okay, so you find those difference between your overall relaxation and
Yeah.
the true shape optimization problem for the third one. But okay, look at again the first eigenvalue, but then in a different case. So you don't put the Neumann boundary condition everywhere. You put part of it with Dirichlet boundary condition, and you don't optimize the Dirichlet boundary condition.
Let's fix. I
Then,
don't know.
okay, my guess would be that you get the same problem.
So I mean, you
The
mean
Dirichlet
that
boundary
you will have
condition-
this phenomenon which will be clear. I also
That's
think
what-
that. So yeah, we didn't try that, but I think that you are right. Yeah.
So thank you again, and we have
Thank
a
you.